started, please. Just to get you all in the right mood, let me give you an exercise. We're in the real line, we're on the real line. We have some subset of the real line. And the claim is that if the supremum exists, then it's got to be, then it has to be in the closure of the set. Okay? If the supremum exists, it must be in the closure of the set. Okay, talk to a neighbor.
It's the line, I'm thinking an interval. Kind of saying is like the close, the set, combined with this limit they will always like is the lever of the set. So it's like a closed set for each. And if the supremum says that there's no flip this way down smaller than infinite. So if you go with anything different than E, whatever, so you can say that's the higher bound, but then it's a limit point. Then it's not the yeah, it has to be C. E bar is the user yeah. I feel like that kind of like naturally makes sense.
That's one thing about real.
It just makes sense. So it's like, well, why does it make sense? Yeah, if you go literally like anything bigger, it's
Okay, let's talk. So the closure is of course the union of the sets, the guys in the set or the limit points, right? So we're saying that the supremum either is in the set or it must be a limit point of the set, right? Okay, anybody want to give it a shot? Richie, go ahead.
So we have that big E is bounded above, and we want to show that for any, so I guess we can, if the supremum of E is in E, then we're done. Otherwise, we want to show that the supremum of E is a limit point. So for any punctured neighborhood, it has to intersect E.
Mm-hmm.
So a punctured neighborhood of, we can show this by looking at open intervals around the supremum of E, but punctured. And for a point less than the supremum of E in there, if it is, I think it has to be in E because if not, or there must be some point in E less than the supremum of E in that interval, because if not, then every point there would be greater than or equal to every, or in fact greater than every point in big E, and thus would be an upper bound lower than the supremum, which is the least upper bound, so contradiction.
Great. You guys see that, right? So you say, well, look, we're trying to show that this guy is in here or in here. Okay. So you say, well, if the supremum, so there's like two cases, right? Either it's in there, right? Either it's in there or it's not in there. Sorry, there's two cases. Either it's an element of E or it's not an element of E. Either it's an element of E or it's not an element of E. If it's an element of E, then you're done, right? If it's not an element of E, then we're hoping that it's an element. Hoping that it's a limit point, right? So here it is, the supremum of E. It's not in E, and you take a punctured neighborhood around it, right? We want to show that it's a limit point. We want to show that every punctured neighborhood must intersect E. So you say, well, if there exists a punctured neighborhood around the supremum such that the intersection it contains no elements of E, right? If that contains no elements of E, well then, supremum of E minus whatever this radius is going to be an upper bound, would be an upper bound. Then supremum of E minus the radius would be an upper bound. Would be an upper bound of E that's smaller, strictly smaller than the supremum. But that's impossible. Right? That's impossible. Okay. Right. So we know that every punctured neighborhood must intersect E, and thus it's a limit point. Any questions? How's everybody? Everybody okay? Okay, I'm going to erase. Okay, so like I said last time, I kind of jumped ahead a bit because I wanted to close on something that was not mind-numbing. So now we have to pay the piper. Okay, so relative relatives. Okay, so you have a metric space X, a metric space, and you have Y, a subset of X. Okay, so X has. I'm going to draw it like this. So here's you can think of X as an example. You think of X as R2, and Y as the x-axis. Say. Okay, so Y is here. It's sitting inside of X, and it inherits the metric from X, right? Okay, so it inherits the metric from X. So it's also, right, is also a metric space. Right? It's also a metric space. But something that's sets that are open in Y are not necessarily open in X. Right? What's an open set with respect to the inherited metric? Like, if we're just talking about we're just talking about Y here. Well, this interval. This interval here is an open set, right? This is an open set, right? I mean, with respect to the inherited metric, right? Every point has a neighborhood that's every point is interior, right? Every point is interior, but this thing is not open with respect to x, right? Because no point is interior, right? No point has a ball that's contained in the set. Is that clear? Is that clear? Okay, right. So sets that are open. So you have to talk about open with respect to what set, right? So you say like so we say we have this definition. E is open. So again, we have the setting, x, y. Y is contained in X, in metric space. E is open relative to Y if, and then kind of what you would expect. If for all points in E, every point is interior, right? So there exists an R, such that the points of Q in Y, whose distance from P is less than R, is contained in E. So I'm just writing the definition of openness, right? This is just this, but just inside of Y. Okay, so you're open relative to Y if you're basically open with respect to Y. Okay, right. So what does that say? That says like, here's my point P, and I'm saying that there's some radius around me that's contained. Every point has a radius around me that's contained inside the set. Right. Okay. Or I could rephrase this as there exists an R such that n's of Rp in X intersect Y is contained in E. Okay, all I'm saying is that there's some ball in X whose intersection with Y is contained in E. It's exactly the same statement. Okay, I haven't said anything yet. Okay. Okay, so then we have this recharacterization of it. E is open relative to Y if and only if E equals Y intersect G for some G that's open in X. Okay, so basically what it's saying is that I have some open set, some set that's open with respect to Y is the intersection of some open set in X with the subset Y. Okay, it's nothing amazing. It just says, look, I can find an open set in X and just whose intersection with Y is my original set here. Okay. You can probably guess how we're created, right? We know that every point here, you can find a ball around it, right? Every point here, you can find a ball around it that's whose intersection is contained in the set. So you just take the union of all those balls, and that's your G. Right? Make sense? I hope that should be pretty intuitive, right? So that's basically the proof. Yeah. So I'm actually not gonna prove it. I'll just the idea is that G is going to be the union of all those balls, right? P and E. So these guys from the definition from the definition of being open, being relatively open, right? Being relatively open means that there's this ball that, you know, blah, 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 blah. So for each point, take that ball, and then take the union of them, and that's the D you're looking for. Okay. Right. And then going back is also pretty much the same. Okay. So I'm just gonna leave that one like that. Okay. Okay. The point of that is to show the following. And like I said, it's kind of an idea that we introduce and then we toss away immediately. So yeah. So the point of it is the following: that compactness doesn't care about, you know, relative or what. If you're compact with respect to the big space, you're compact with respect to the inner space, and vice versa. Okay. So compactness is independent of the embedding space. Okay. So the setting is this: you have some axisymmetric space. You have some subset. You have some subset inside of it, and we have what's going to be a compact set sitting inside of that guy. Okay. So the claim is that K is compact with respect to X, if and only if K is compact with respect to Y. Okay. So once we say compact, we don't have to worry about what space we're talking about. It's compact. Okay. Whereas if we're talking about open, we have to say open relative to what, relative to what space. Okay. So let's do this. Right. Right. So compact with respect to. Is there a question? Do you have a question? No, you didn't. Okay. So okay. So suppose that K is compact with respect to X, right? It's compact with respect to the big space, right? And we want to show it's compact with respect to Y also. Okay. So right. So assume K is compact in X. Want to show K is compact in Y. Oops. In Y. Those of you who like obscure notation, sometimes people write compact like this. So K is compact in Y. I've seen it, but I've only seen it like once or twice. Okay, so we want to show K is compact in Y. What does that mean? What does it mean to be compact in Y? That. Go ahead.
There's a finite cover of X.
For finite cover of K, but you have to put in the beginning part, like given any cover, there's a finite cover.
Okay.
Yeah. So you say we want to show that given any cover. Given any open cover, G alpha, okay, there's this a finite subcover. Okay, there's this finite subcover. Okay. Yeah, it's really this thing that you can always go for whatever open cover you've got. There's always a finite subcover. Okay, so it's a quality of the set. Yeah, Rishi.
And here, since we're in Y, these have to be open with respect to Y, right?
Yep.
Like as a subset.
Yeah. So given any open given any open cover of K and Y, there exists a finite subcover. Right? There's a finite subcollection of these guys that still covers it. Okay. So we know that we can do this sort of game in X, right? Right? So what we have right now, we have our set K, it's here. We have some cover of it. It's an infinite cover. Okay. There's this infinite cover of it, and we want to show that it's got a finite subcover. Okay. We know we can do this in X, and so what we do is we pass up to X, right? So remember what we just said. We had this thing that, you know, set is open in Y if and only if it set S is open in Y, if and only if S equals Y intersect G for some G open in X. Right? Every set that's open in Y is the intersection of some set in X with Y. Okay, so we'll just use that to pass up to X, right? Right, and then what are we going to do? Turn to a neighbor and say, once we do that, it's basically over.
It's basically over.
And then we just take that cover and how it intersects with like the line and line. I think that just make it a cover. The line ends up intersecting with the line. To keep it
Yeah, when someone else comes up with the idea, I'll be like, oh my god, I came up
all
with
you have to
this.
do is intersect all those covers with the line, and it works out perfectly.
Okay, so right now, right, we've got this open cover. These guys, you know, cover K, and each of them is open in Y, and we're going to pass each of them upwards, right? So by the theorem, each G alpha equals what should I call it? Equals some open set in X intersect Y. Right? Each of those guys is actually it's actually the intersection of some open set, right? Just to balloon each of them outwards. Each of them is an open set in X, right? Intersect Y. Okay. Okay, but then the H alpha are an open cover of Y, of K in X. Right, so now we've got an open cover of this guy in X, right? Which is good because then we can, what do we do then? We say, well, look. What do you say? Yes? There's a finite subcover, right? K is compact in X. We assumed it was compact in X, so there's a finite subcover, right? K compact in X implies there exists some H alpha 1, H alpha 2, H alpha n. There exists some finite collection that covers K. Right? There exist indices alpha 1 through alpha n such that, right? So, right, once we pass up to the thicker space, we can say, okay, there's actually only finitely many guys who cover your K, right? But then you just intersect back down, right? So then K is included in H alpha 1 intersect Y, right? Is included in Y intersect this thing. right? But that's the same thing as the union of y intersect hi as I goes from 1 to n. Okay, and each of those is your G alpha, right? So that means that we found, right? Right, so we found the finite subcover, right? We found the finite subcollection that still covers K. Okay, so no matter what open cover we started off with, we can find a finite subcover. The set is compact. Okay, if we want to do the backwards direction. Do you guys want to see the backwards direction? It's pretty similar to the forwards direction. I'm going to skip because it's basically, it's a very similar argument, and let's get on to the other arguments that we should get to. Okay. So, exercise for the reader, as they say. Okay, let's okay, yeah, let's get on to the water. Yeah. Close your eyes for a second. Raise a finger if you want to see the backwards direction. Okay, put your fingers down. There's this kind of a. Well, let's do it. So, okay. So, let's do the backwards direction. So, assume K is compact in Y, and you want to show K is compact in X. Okay. So it's compact in Y. So say, okay, what do we want to show? That it's compact in X. So given an open cover in X, right? Of K in X. Right, we want to show that there exists a finite subcover. Right. Okay, so probably write down something like, what do you think the strategy is going to be? Take 30 seconds and write down, oh, we're going to do this sort of thing, and it's going to work out. Right, so K, remember, K is right now, oh no, K is a subset of Y. Right. We have an open cover in X. How many of you pronounce this differently from this? These two words. Same? Interesting. Why? I don't know. I was born in North Carolina. I think it is a southern thing, maybe, to pronounce to pronounce Y different from Y. But yeah, if I may tell kind of an amusing story just to entertain you. When I first, I don't know if I've told this story, I don't know if some of you have heard this before, but when I first started teaching at the University of Chicago, like at the very beginning, after a few weeks, the administrator in charge of the graduate student teachers came to me and she put her hand on my shoulder and she said, Winston, you know, a student came to me today and he said that he has to drop out of your class. And I was like, okay. And he said, it's because he cannot understand your accent. And I'm like, I was born in North Carolina. Do I still have my North Carolina accent? And she said, you know, I told him that I know Winston O, and he doesn't have an accent, but he said, no, he has a very strong Chinese accent. And I have to drop out of his class. And so she let the student drop out of the class. So, yeah. There's actually some like linguistic studies about this, how people's perception, right, can really skew. Like they have a picture, they have a movie where they've dubbed it of a Chinese person, but they've dubbed it over with a native American, a native English speaker's English. And conversely, they take the American person and dub it over with the Chinese person's English. And people say, this person I can't understand, and this person I can understand. So it's kind of interesting. But anyway. Okay, so what's the step? What are we going to do, right? We want to show we have a finite subcover. We're going to...
Do we intersect with y, show it works, and then go back up to
Exactly. Yes, that's exactly it. So we intersect down to y. We know it's compact. We know that it's compact in y, so there's a finite subcollection there, and you just pass back upwards. So let me write it down just to be proper. So consider G alpha intersect y, right? Right. These are open sets in y. Open sets in y that cover K. K is compact in y. So there exists some finite subcover. A finite subcover. Right, finite subcover. So then, certainly, the union of the G alpha, from I equals 1 to n, still covers K, right? Because the union of these intersected sets, covered K. Well, if we blow it up even bigger, it's still going to cover K, right? So we're done. So we're done. Okay, everybody all right? Any questions? Oddly, my girlfriend at the time was a biology graduate student, and she had some of the same students, and she said to them, does Winston O have an accent? These students were from Korea, and the students in common were from Korea, and they said, yes, he does, but we're from Korea, and so we can understand him. I should revive my North Carolina accent, is what I should do. Yeah, my math teacher in high school had a very strong North Carolina accent. He'd be like, suppose you've got a wire. Suppose you have a wire. A wire? Right? But that's how he talked. Yeah. Okay, let's go on. So what we're going to show now is that any closed subset of a compact set is compact. So any closed subset of a compact set is still compact. Okay. So we have F contained in K, contained in X. People always use F for closed sets because of French closed. And so we say if K is compact and F closed, then F is compact. Okay, so we have our compact sets. We have our compact set. We have our ambient space X, right? And inside of X, we have some closed. Inside of K, excuse me, we have some closed set F. We want to show that that guy is compact. Okay, and the proof is proof goes like this. You say, well, suppose you have an open cover, G alpha, an open cover of F. Okay, so you have some open cover of F. Okay, you have some open cover of F, yes?
Here is, F is closed relative to K, right?
F is closed in
Because the situation I'm imagining is if it's like on the, it's like pushing up against the edge of K, like the boundary of K, such that it would be like the intersection of, like the complement would be the intersection of an open outside of K and K, or something like that.
Let me think for a second. F is closed in X is what we assume.
Okay.
Yeah, F is closed in X. Yeah, F is closed in X, sorry. Okay, so we have some open cover of F, right? And we want to show that we can get a finite subcover of it. Okay. So what we're going to do is take advantage of K, and we say, okay, so we'll extend the open cover to an open cover of K, and then we'll use the compactness of K. So that's the strategy, right? So we'll extend, throw in some more set, throw in one more set, and that will give us an open cover of K, and then we can go from there. Okay. So, okay. So then, if we consider F complement is open. So if we consider the G alpha guys plus F complement, that is an open cover of K, right? I mean, in fact, it's an open cover of the entire space, right? Open cover of X, and certainly one of K. Okay. So then, K is compact, so there exists some finite subcover. G alpha 1 through N, and maybe also F complement. It may be there, maybe it's not in there, who knows? Okay, but in any case, you're gonna have, there's a finite number of sets here. Okay, so this finite collection covers K, right? Covering K, and so these guys, these guys cover F, right? These guys cover F. We can throw out the F complement. We don't need that to cover F. It doesn't touch F at all. It's F complement, right? So we know that all these guys cover K. So these guys only from G still cover F, right? And so we have a finite subcover for F. Okay, so F is compact also. Okay. Okay, everybody okay? Okay. What we're really trying to head for is something called the Heine-Borel theorem. So if you're wondering, like, what are all these kind of odd little facts? Yes, Harrison.
Why did you write the union of that and F complement though?
Well, because this thing here is my open cover, right? This is my open cover of K. That's my open cover of K. I'm using the compactness of K, right? So I have to use the compactness, I have to have an open cover of K. So I had to throw in this F complement to cover K, because my cover of F might not have covered K, right? So I throw in F complement. Now I certainly have covered K, because I've covered the whole space, right? So now I've got this cover of K, and now I've got a finite subcover of K, right? Now I've got a finite subcover of K, and I say, okay, that thing is still going to cover F, and I don't. If this thing may or may not be in there, but whatever, I throw it out. When I'm thinking about F, I definitely don't need it, right? So I've gone from my initial open cover of F to a finite subcover of F, which is what I needed to show compactness. Yeah.
So if F were an open set, I just didn't see how there's a finite cover of K, right? How would F being open mean that finite cover wouldn't also cover F?
Yeah, well, if F were open, then I wouldn't be able to. I wouldn't have a cover. I wouldn't have an open cover of K anymore, right? Because F complement would be a closed set,
Okay.
right? So I can only invoke the compactness of K when I'm going from an open cover of K to a finite subcover, right? But if F were open, then when I make this move, I'm throwing in a closed set, and K would be like, I'm compact, but I can't do anything for you, right? Okay. Other questions? Okay. So yeah. So like I said, we might look like we're doing all these kind of like odd peculiar facts. The real goal here is to get to this thing called the Heine-Borel theorem, which says it gives a characterization of compactness in Rn. It shows that compactness in Rn is equivalent to being closed and bounded. Okay, so there's like a nice characterization of compactness in Rn, and we'll also at the same time show something that this kind of compactness is equivalent to something else called limit point compactness. Okay, which I'll talk about pretty soon, I think. Okay, so it might seem like what are all these little results, but we need all those little results to get to this big result. Okay. Okay. So. Okay. Yeah, and basically the sort of sub-result that we're going to need to get there is this one, that K cells in Rn are compact. So any parallelepiped in Rn is compact. Okay. So that will be a big tool to get there. Okay. Okay, so let's see if I can lay this out clearly for you guys. Okay, so right now we're going to prove another property of compactness. Another property of compactness. Actually, let me make a terminology. We'll say a collection of sets. G alpha, say, has the finite intersection property if every finite subcollection has a non-empty intersection. Every finite subcollection has a non-empty intersection. Okay. So for example, if you have nested intervals, where you have some nested intervals, okay, then when you intersect finitely many of them, you're just going to end up with the smallest one of them, right? And that will be non-empty, right? So nested intervals, or indeed, any nested sets, nested sets at all, as long as none of them is empty, right? If you've got a bunch of sets and they're nested, whenever you intersect finitely many of them, you're just going to get the smallest guy, right? So these guys have the finite intersection property, right? But if I have something like a set here, and then these guys, say, I've got a bunch of nested guys, and then I've got this set over here, well, whenever I throw this guy in, the intersection is going to be empty, right? So this is this thing down here doesn't have the finite intersection property. Okay. Okay. So here's the theorem that if you have compact sets, so X, again, metric space, and then you have some collection, K alpha, compact sets in X. So if the K alpha has the finite intersection property, then the infinite intersection is also non-empty. Okay, so for compact sets, whenever you have the finite intersection property, then the infinite intersection is also non-empty. Right? That's not true for open sets, right? If I take, from 0 to 1 over n, right? And I intersect all of those guys, well, there's nobody in that. There's nobody in the intersection, right? Even though they satisfy the finite intersection property, when I intersect all of them, it's empty. Right? So fails for, say, open sets. Okay. Okay, so the proof is, we're going to do it by contradiction. So suppose that the intersection is empty. Okay. In that case, the complement of the intersection is the whole space. Right? The complement will be the whole space, but the complement of the intersection is the union of the complements. Right? The union of the complements by De Morgan's laws. Okay. In that case, we have a cover of the whole. We have, each of the compact sets, remember, is closed, so their complements are open, and so we have an open cover of the whole space. We have open cover of X. Okay. So now fix some K naught. K alpha naught. Okay, so choose one of those. Choose one of those guys, right? And consider yeah. So K alpha naught is contained K alpha naught is covered by this, right? Since we have an open cover of K alpha naught, there exists a finite subcover. So K alpha naught is included in some union K alpha 1 complement K alpha alpha n complement. Okay, so far so good? Okay, so in that case, if we look at K alpha naught intersect the complement of those guys, right? So K alpha naught is included, K alpha naught is contained inside this set. So its intersection with the complement of that set will be empty. Right? But again, by De Morgan's laws, the complement of a union is the intersection of the complements. So here we get the intersection of the complements. Okay, and so what we get is we get K alpha naught intersect K alpha 1, intersect K alpha n is empty. Okay, but that means that we failed the finite intersection property. And we said at the beginning that we have the finite intersection property. So there's a contradiction. Okay, I don't really like this proof, but I hope everybody sees that it works. Okay, is it any questions on any step? Yes, Harrison.
Yeah. I'm not exactly. Repeat that last part.
Yeah. So De Morgan's law says that the complement of a union is the intersection of the complements.
Yep.
Okay, so here we get the intersection of the complements, right? But the complement, right? The complement of the complement
itself
is just the original, right? And so we get K. We get this is empty. Right? The intersection of these finitely many K's is empty. But we assumed at the beginning that the K alphas had the finite intersection property, that any finite intersection of them was non-empty. Right? That's this thing here. Right?
Oh.
Every finite intersection is non-empty. right? And here when we assumed that the infinite intersection was empty, that forced a finite intersection to be empty. Okay. 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 Two more. So hang in there. I can see that the energy level is flagging. Hang in there for two more sort of like two more results, and then we'll do something extremely cool. Okay. Theorem. Okay. So suppose you have E a subset of K, and E is an infinite set. Okay. Then if K is compact, then E must have a limit point in K. Okay. So whenever you have a compact set and you've got an infinite set of points inside of that compact set, then there must be some place where there must be some limit point. There must be some limit point for those guys. Okay. This is called the Bolzano-Weierstrass property. I guess maybe I should define it here. So if a set has the property that every infinite subset has a limit point, we call it limit point compact. Or sometimes people call it Bolzano-Weierstrass compact. Okay. So what we're showing here is that compact implies limit point compact. Okay. So compact implies limit point compact. Okay, and later we'll see that the opposite is also true. Okay, so we're going to do this by by contradiction again. So suppose no point in K is a limit point of E. Okay. No point in K is a limit point of E. Okay. In that case, then for each, right, no point in K can be arbitrarily finally approximated by points in E. Right. Then for each point K, what do I call in the notes? Q, for each point Q in K, there's going to be some punctured neighborhood around it that doesn't intersect E. Right? So every point in K has some little neighborhood around it that the puncture of it doesn't intersect E. So in other words, it intersects E in only possibly the center, the one point, the center. Okay. So every point in K, we can find a little neighborhood around it in which there's at most one point of E. Write down something. What's wrong with that? What's wrong with that? See how you can bring in compactness into play here. Right? Every point has this neighborhood in which there's only one point in E. Or maybe I'll just make you do it. Okay, so I'll make you do it. So compactness, right? How are we going to bring in compactness? Every point has this neighborhood. What are we going to do? Anybody have any idea what we'll do? We'll cover K with all those neighborhoods, right? Every point of K has such a neighborhood. We cover K with all those neighborhoods. Okay, right? Then we take a finite subcover, right? There's only finitely many neighborhoods now. How many points of E are there? Infinitely many. How many points of E are there? Finally many. Contradiction. Okay. Okay. So you say, okay, look, cover K with the NRQ. And to be proper, I should probably say n sub RQ of Q, right? Because the radius depends on Q. Cover this with these guys. K is compact, so there exists. So we know that there's finitely many points Q1 through Qn, such that K is covered by those finitely many neighborhoods. Right? But then the number of points of E has to be smaller than the number of those points. Contradiction. Okay, last peculiar fact. Suppose you have I sub n, a nested sequence of intervals, of closed intervals in R. Okay, so I sub n, let's say they are A sub n, B sub n, right? So you've got these nested intervals, right? I1, A1, B1, A2, B2, A3, B3, and so on and so forth. Okay. You've got a bunch of nested intervals. Okay. Then the intersection of the IN is nonempty. Okay. So if we knew that the IN were compact, then we could say, okay, we know that nested compact intervals have a non-empty intersection, but we don't. We don't know that the IN are compact yet. In fact, we're going to use this to show that the Heine-Borel theorem, which would allow us to say instantly that these guys are compact. Okay, so it's kind of that's kind of the line of the argument. Okay, so let me sketch out the proof here. Okay, we want to show that the intersection is non-empty. The strategy is that we're going to take the supremum of the left intervals. I'm sorry, the left endpoints. Okay, and we'll say at that point the supremum of the left endpoints is in the set. Okay, so let E be the union of all the left intervals, left endpoints, excuse me. Okay. Let E be the set of all left endpoints. Okay. Any BI is an upper bound of E. Right. Any BI is an upper bound of E, and so supremum exists. Okay, so our claim is that the intersection of the IN must contain that supremum. Okay. Okay, and the way you see it is that, well, right, the supremum of E, for any endpoint, AI is going to be less than or equal to the supremum of E, right? Because it's the least upper bound of these guys, right? It's the least upper bound of them, so it's greater than or equal to all of them, right? It's the least upper bound of the endpoints, the left endpoints, right? Okay. Further, the supremum of E is the least upper bound, right? Is the least upper bound. So it's less than or equal to any of the BI because each of these guys are upper bounds of E, as we said. Right? Each of these guys is an upper bound of E, and this is the least upper bound, so it must be less than or equal to all of them. Right? So this is for all I. Okay, so what do we have? That supremum of E is in every interval, right? And so it's in their intersection. Okay. Okay, and remark, you can do this for K cells as well. Right, that the intersection of nested K cells, right, if you have intersection of nested K cells, is going to be non-empty. Okay, all right, 4 minutes. I don't know if we can do it, but I'm going to see if we can. Okay, so here is finally the interesting, the sort of cool proof. That claim is that all K cells are compact. All K cells are compact. Okay, so here's the proof. Let I be a K cell that's going to be a product of some intervals, BI, AI BI from I equals 1 to n, from I equals 1 to k, because this is a K cell. Okay, so let delta be, you take the length of each interval and you square it, okay, and then you sum all those lengths, I equals 1 to k, and you take the square root of that. Okay, that's the length of the diagonal from one corner to the opposite corner. Okay, like if you're thinking about, in a 2-cell, right, it's just the Pythagorean theorem, right? It's this squared plus this squared rooted, right? And similarly, if you go into higher dimensions, it's just the distance between corners, opposing corners. So the length of the diagonal, aka sort of like the diameter, the greatest distance between points, aka between 2 points in K. Right? Nothing is going to be farther apart than those points at the corners, at opposing corners. Okay, so our claim is that we want to show that that the K cells are compact. So we'll do it by contradiction. Suppose the K cell is not compact. I is not compact. Okay. In that case, and I'm just going to draw it as if it were on the plane. So you say, okay, suppose we're not compact. What does that mean? If you're not compact, then there's some cover that doesn't have a finite subcover, right? I.e., there exists a cover G alpha, for which no finite subcover is given. Right? No finite subcover is going to cover I. Okay. There exists a bad cover. Okay. So now what we do is we divide this guy into dyadic subsets. Dyadic just refers to the number 2. We divide each side length in half. Okay, and then create these. Create 2 to the k subcells. Okay, so you create 2 to the k child cells. Okay, and you know that at least one of them, must not have a finite subcover. Right? At least one must not have a finite subcover. Right? Because if they all have finite subcovers, then I must have had a finite subcover. Right? So there's got to be a bad child. In other words, there exists a bad child. Okay. Let's say it's this one. Okay, and let's call that one I2. Call this one I1. Okay. Iterate. I2, must have a bad child for the same reasons, right? I3, etc., and so on and so forth. Right? So you create a sequence I sub n of bad family, of bad cells. Okay, generation after generation. Okay, right. Now the intersection, as we just said, the intersection of those guys is not empty. Right. So let. And in fact, it consists of a single point because the diameters are decreasing to 0, right? So there exists a single point x star that is in the intersection of all of them. Okay. Okay. So now, but x star must be covered by some g alpha. G alpha star, right? Because the G alpha is covered the whole thing, so that x star, wherever it is, it must be covered by some G alpha, right? G alpha is open. G alpha is open, and so we know that x star lies inside some interval, lies inside some neighborhood that lies inside of that G alpha. right? Because it's open, right? X star is interior to G alpha, right? Okay, so we know that here's X star here, right? And we know that there's some open interval around it. Here's where the contradiction comes, and I'm sorry to keep you over. Here's where the contradiction comes. Eventually, right, for big enough n, I sub n, the diameter of I sub n is going to be smaller than r, right? Because the diameter of I sub n is like the diameter of I sub n is like this divided by 2 to the n. Right? It gets halved every time, the diameter. Right? So what does that tell you? That tells you that that I sub n, I'll call it n naught, the I sub n naught must lie inside of that ball, right? But that means it lay inside of G alpha, which means that it wasn't a bad child. It was actually covered, right? So the one that we said that all these guys are bad, but in fact we found one that's actually good. Contradiction. Okay, that's it. Sorry to hold you.